buffer is an aqueous solution containing both a weak acid and a weak base that are a conjugate acid-base pair. The buffer shown contains the weak acid acetic acid and its conjugate base acetate. These species are dissolved in water. Water molecules are not shown in this animation to draw focus to the buffer components. A buffer solution has the ability to resist changes in pH upon the addition of small amounts of either acid or base. Choose to add a strong acid or a strong base to the buffer by clicking one of the buttons.
So this is our weak acid. This is the acetate ion it breaks into. Now remember, it is going to be an equilibrium arrow. So I'm going to add a strong acid, and remember, strong acid means that it's going to be completely dissociated into the H plus and whatever's left over. So you're going to see a pipette. He's going to drop in some strong acid, and again you're going to see that only the H plus is really what's necessary. So in the graph, he's going to show you the H plus being added and what happens to that H plus, who it reacts with, and what happens to the two components, the weak acid and the conjugate base.
Only hydrogen ions, H+, from the hydrochloric acid are shown entering the solution. Chloride is not shown because it is a spectator ion. It does not participate in the reaction. The strong acid H+, reacts with the base component of the buffer acetate, CH3COO-, producing the acid component of the buffer acetic acid, CH3COOH. The buffer has resisted a change in pH by removing strong acid, H+, from the solution.
So hopefully that makes sense. So we added the H+, it reacted with the base, the conjugate base component, pushing the reaction to the left to form more weak acid. If it's forming more weak acid, it's going to resist that change in pH because there's no H+ acid to make it stronger. It's all used up. So now let's add the strong base. Again, he's going to add some strong base. In this case, it's going to be slightly different. Yes, it's going to completely dissociate into the OH-, but there's going to be a new substance that actually is going to be formed in the beaker. So you're going to look here at the graph to the OH. It's going to go back to the original, add the OH-, and see now who it reacts with and why and how it resists pH change.
Only hydroxide ions, OH-, from the strong base sodium hydroxide are shown entering the solution. Sodium ions are not shown because they are spectator ions. They do not participate in the reaction. The strong base hydroxide, OH-, reacts with the acid component of the buffer acetic acid, CH3COOH, producing the base component of the buffer acetate, CH3COO-, and water. This buffer has resisted a change in pH by removing the strong base, hydroxide, from the solution.
So because the base is so strong, that OH- is going to react now with the weak base, and again it's going to push off that H+ from the weak acid, and so we're going to get the H and the OH coming together to form that water. So that's part of why that change in pH is resistant. And also again, so look here, you're forming more of that weak conjugate base. There's no more OH- in here, so that's why it resists the change in pH overall.